Hi everyone, in this example we are going to be solving another problem involving the circular motion of a charged particle through a magnetic field. And you will see this one is quite interesting. It involves a little bit of geometry. So this question 184, let's read the question. Question 184. A proton passes through a region with a length of 0.35 meter with a magnetic field of 0.2 Tesla. Calculate the velocity of the proton, magnitude and direction, and the time spent inside the magnetic field. So we are shown a diagram. We have a proton coming with a velocity of 10 to the power 7 meter per second. It enters a region with a magnetic field pointing into the board. And the magnitude of this magnetic field is 0.2 Tesla here. Now, because the charged particle is not at rest and there's a magnetic field that is perpendicular to the velocity, it will start curving and following a circular path. We are asked to find the velocity when the proton exits the region with the magnetic field and its angle over here. Now, it's a bit tricky. The first part is we should find the radius of curvature first. So again, we use that formula, the charge multiplied by the velocity multiplied by the magnetic field. Note, the sine 90 is missing, but it is equal to 1, so it does not even matter. We want to find the radius. We plug all the value that we have, and we find a radius of 0.52 meter. All right, so what's happening is we have a certain point that will be the center of curvature. And from the point where the proton is entering the region with the magnetic field, the distance is 0.52 meter. When it exits the region with the magnetic field, it is still at 0.2 meter from the center, center curvature. All right. Now, because of this, we can create a triangle over here with this curve, and the angle of this triangle, this angle over here, will be the same as this one. Okay, that might not be obvious at first, so let's visualize why this is the case. We have the velocity over here, and the proton is curving, curving, and curving. Well, note, every time you're moving 1 degree in that direction, this one is going down also 1 degree. In all cases, the radius and the velocity are perpendicular at all time, so the angle over here is identical to this angle. Well, this angle we can easily find. This side over here, we've been given that is 0.35 meter, and we just calculated this side, which is the hypotenuse of our triangle. So if we want to find the angle, so in part A, actually there's no part A, it's a different step. So I'm just gonna replace A, B, and C for the step 1, 2, 3 actually. 1, 2, and 3. There we go. All right. So at the first step is we're going to find the exit angle. So the angle in this case will be the inverse sine function of the opposite side, which is 0.35, divided by the hypotenuse, 0.52. And we get an angle of 42.03 something, so around the value to 42 degree. All right, now at the beginning of the chapter, I mentioned that the magnetic force, because it is perpendicular to the displacement, never does any work on the charged particle. Well, if there's no work, there's no transfer of energy. If there's no transfer of energy, the kinetic energy does not change, which means that the velocity has to be at all time zero. Has to be the same. The change in kinetic energy has to be zero, sorry. So in this case, the final velocity has to be the same as the initial velocity. And by the way, in a test, if I ask you this question regarding the velocity in a magnetic field like this, and if there's no electric force involved, well, the final velocity has to be exactly the same. All right, so we got the final velocity, we got the angle over here, so we got our final velocity vector. The last part is we are asked to find the time spent inside the magnetic field. Well, the answer from the second part, the final velocity, 10 to the power 7, and the initial velocity, like I mentioned, the velocity stayed the same throughout the entire motion, so we just need to find out what was the displacement around this circle. Well, what we can do, and what we need to do actually, is we need to find the angle in radians. So we have the angle in degree, 42 degree. So we convert it in radian, so 42 multiplied by pi divided by 180 degree, we get 0.733 radian, all right? If we want to find the displacement around the circle, we multiply the angle in radian, multiply by the radius. We get a displacement around this circle of 0.38 meter. At this point, it's fairly straightforward. The time is equal to the displacement divided by the velocity, and we get a time of 3.81 multiplied by 10 to the power minus 8 seconds. All right, so the concept in the magnetic field section here, they are not too complex. There's some geometry involved, and in the test, you might have to do something like this where you need to draw a triangle. So there's no avoiding using trigonometry in this course, all right? So we are done with question 184. Let's switch to the velocity selector, and in the next example, we're going to explain how such a device works. All right, see you in the next video.